Today we are going to discuss the interference of light. Now this is a superposition principle that whenever two or more than two waves superimpose on each other, the resultant pattern can lead to different types of phenomenon in light. The first one we are going to discuss is interference of light. The term interference refers to the phenomenon involving superposition of waves leading to a modification of their intensity in the region of superposition. When two or more than two waves superimpose on each other, then having same frequency and same wavelength in the same direction, the resultant pattern so obtained is known as interference of waves. Now, interference is of two types: constructive interference and destructive interference. When intensity become more than the sum of the intensities of the individual waves, it is known as constructive interference, where crest of one wave falls on the crest of another. And at a certain other point, it may tend to zero, which is called as destructive interference, when crest of one wave falls on the trough of another. Now, you can see that the two waves, top and middle one, arrive at the same point in space. The total wave amplitude is the sum of the two waves. You can see that one wave plus second wave gives you constructive interference. The total amplitude increases, which is sum of the amplitudes of these two waves. But when crest of one falls on the trough of another, you see that if they have the same amplitude, the resultant amplitude is zero. Now this is called as what? Destructive interference. Now when waves from two or more sources arrive at a point in phase, they reinforce each other. The amplitude of resultant wave is a sum of amplitudes of individual waves. This is called constructive interference, which will show in that diagram. If the distance of any point P from the two sources is R1 and R2, then for constructive interference, the path difference must be integral multiple of wavelength. That is, the path of the second wave minus path of the first wave, and that should be integral multiple of lambda, where n stands for 0, 1, 2, and so on. Now points A and B in the figure below, which we are going to show it just now, satisfy this equation for n is equal to 0 and plus 2 respectively. If you can see this, the two coherent wave sources separated by a distance 4 lambda. Then the waves spread out from the two coherent sources S1 and S2. Constructive interference occurs at point A and destructive interference that occurs at the point B. If you see that the blue lines, they represent crest, the green lines represents the trough. Similarly, you can extend this at any point. All blue lines interfering gives you constructive interference. Blue and green interfering gives you destructive interference. Now condition for constructive interference. When the path difference is integral multiple of wavelength, then constructive interference takes place. That is, for example, if this path followed is 9 lambda, this path followed is 7 lambda, the difference between the two is 2 lambda. Condition for destructive interference, when the path difference is half integral multiple of wavelength. That is, one is say 7.25 lambda, another has traveled a distance and 9.75 lambda. The difference between the two, that comes out to be fractional one. Now the condition of destructive interference is the path difference is equal to n plus half lambda. N stands for 0 plus minus 1 plus minus 2 and so on. And the path difference in point is for n is equal to minus 3. Conditions for interference of light. The sources must be coherent. Now what are coherent sources? those which give out light of same frequency, same wavelength, and in the same direction. They must maintain a constant phase with respect to each other. The waves must have identical wavelengths. Two sources must be narrow because a broader source of light is equivalent to a large number of narrow sources. Sources should be monochromatic, that is, having single wavelength. Distance between two sources should be very small. Wavelength of two sources should be same. Amplitude of wave should be same. Wave should be in the same state of polarization. Now, what is coherence? The term coherence refers to a degree of correlation between the phases at different points and different times in a beam of light or radiation. Temporal coherence or longitudinal coherence. A beam of light is said to be temporal coherence if the phase difference of the waves crossing the 2 points laying along the direction of propagation of the beam is independent. For this reason, the temporal coherence is also called longitudinal coherence. Now you can see that this is temporal coherence. Here is that path R. This is the path T2. This is the next one, and so on. In order to understand the concept of temporal coherence, let us consider Michelson interferometer arrangement as shown below. The source is extended and near a monochromatic source of light. Light from this source falls upon partially coated glass plate A, which is divided into two parts on the towards mirror M1 and mirror M2, which are at equal distance from the point A. That is, when two waves traversing the two different paths take the same time, the interference pattern formed is very good. If the mirror M2 is moved very slowly, you can see that this mirror is moved towards that point A. The light is going from here, part of that goes to this direction, part of that goes to this. The light is reflected back, and so on. Then it's seen that for the ordinary extending source of light, the contrast in the fringes goes on decreasing and finally disappear when the path difference AM1, AM2 is about a few mm. What is AM1? You can see that. This is AM1 and this is what AM2. The source S is emitting small wave trains of average duration tau-c, and there is no relationship between the wave trains. When the difference in time taken by the wave train to travel the path A to M1 and back and A to M2 and back is much less than average duration tau-c, the interference is observed between the two wave trains is one being derived from the same wave train. Hence, even though different wave trains originating from the same source have no definite phase relationship, but since one is superposing the two wave trains derived from the same wave train, therefore fringes of good contrast are seen. On the other hand, if the difference in time taken to cover the path to M1 and back to M2 and back is greater than tau-c, then one is superposing two wave trains which are derived from two different wave trains. Interference fringes are not observed since there is no definite phase relationship between the two wave trains emanating from the source. Hence, if the mirror M2 is moved, the contrast in the fringes goes on decreasing, and for large separations, no fringes are observed. Let D is the distance through which mirror was moved when no fringes would be observed. The beam which is reflected from mirror M2 travels an additional distance 2D. Thus, beam reflected from M1 originates 2D by C seconds earlier, interfere with the beam reflected from M2. If D is distance such that 2D by C is greater than or equal to tau-c, then no interference will exist between the two beams, therefore no fringes are observed. Spatial coherence or transverse coherence. A beam of light is said to be spatial coherence if the phase difference of the waves crossing the 2 points laying on a plane perpendicular to the direction of propagation of the beam is time independent. Now you can see that double slit experiment for studying the spatial coherence for a light source. That source S, light is going on this, a double slit, one slit here, another slit here. After that, superposition takes place here. Two pinholes S1 and S2 on screen are such that their distance from the point source S and distance from any point O on the screen are equal. Since point source S illuminates the pinholes